Hello everyone, welcome to 2.2 Forces video 2 of 2. This is the slide that we left off with last time. We finished it, we figured out the weight, the lift, drag, and thrust force on an airplane. So the only thing that you didn't see in the slides was this final piece put together. So instead of having the forces acting just on the plane, this is just the representation of them acting as if the plane could be represented with a single point. Okay. So in the last video, we looked at Newton's first law of motion. In this video, we're going to be looking at his second and third laws, starting with the second law. And there are three laws, so in case you're wondering. All right, so Newton reasoned that if the sum of the forces is not zero, then the velocity will change. And what we saw last time in the first video with Newton's first law was that if the forces were balanced and an object was in equilibrium, even translational equilibrium, if it was moving and the forces were balanced, then the velocity was constant. And of course, if it's still, then the velocity is zero. Right? So Newton also understood that if an object changes its velocity, that means it is accelerating. And that's whether it's speeding up or slowing down. They're both called acceleration. So then what do forces have to do with acceleration? Well, he realized that if you have two objects that have the same mass and you apply different forces on them, the one that you apply a larger force on will experience a larger acceleration. And likewise, if you have two different objects, different masses, let's say a bowling ball and a tennis ball, if you apply the same force onto them, the object with more mass will accelerate less. So we saw that there was some kind of relationship there. Okay, so Newton's second law says that acceleration is the ratio of net force to mass, or said another way, F net equals ma. So this is Newton's second law right there. It is the mathematical law. To remind you, Newton's first law is the law of inertia. Now, because I can write F net a different way, I can write it as sigma F, or the sum of the forces. Just make sure you understand that those two are the same thing. Okay. Now, something to note, and this is what we saw last time, if acceleration is zero, in other words, velocity is constant, then the sum of the forces is zero, and that's exactly how we solved our problems last time. In this video, we're going to be solving problems very similarly, except this time, the sum of the forces is not going to equal zero, it's going to equal mass times acceleration. Excuse me. Now, the mass is usually given to us, and acceleration is either given or we can find it. Right, so remember, if acceleration is zero, velocity is constant. And that's a special case of Newton's second law. Okay. All right, so let's keep going. This is, by the way, probably the most important formula that you're going to see in all physics courses. F net equals ma. It's so significant, it keeps appearing every single time. Actually, this would be a good time for me to pop back to the formula sheet for a moment. So hopefully you have that with you. So remember, we're doing section 2.2, so we're in box 2.2. The first formula there is F equals ma. F, even though it doesn't say F net or sum of F, this is a net force. So when you see F equals ma, you cannot calculate just any force like this. Okay, this means it has to be the total forces acting on an object, so F net. So again, even though the subscript's not there, you have to understand that it really is. Okay, let's do this problem. An object has a mass of 25 kilograms, a tension of 50 newtons, and a friction force of 30 newtons, and they're acting on it as shown. What is its acceleration? We actually did this problem before. Excuse me. So we're going to go ahead and quickly do it again. So I'm going to be going through it a bit faster than before. If you are finding that it's a bit too fast for you, I would really encourage you to go back to the previous video and review the problem so you can see how it's done. Okay, so I'm going to quickly sketch this out. So we've got our box, we've got our weight going down from the center, reaction going from the surface, friction between the two surfaces in parallel. So that's FF, this is W, this is N, or you can call it R, and that's T, tension force. Okay, tension's 50 newtons. I know in my slides, the newtons is in lowercase n. Some books do write it with lowercase n. Sometimes it's lowercase, but usually it's uppercase. So just keep that in mind. I would keep it uppercase if I were you. Okay, so we're looking for the acceleration. Now, I just saw Newton's second law tells me that the net forces acting on an object is equal to its mass times its acceleration. And I'm given the object's mass too. It's 25 kilograms. So I have m, I can find a as long as I have the net forces. And we did this earlier. Like I said, in the last video, we solved this. Since we're dealing with the x and y directions here, I'm going to define my positive x and y directions. So up and to the right. In the y direction, the normal force and the weight balance each other. Okay, that's not always the case, but it is in this case. They balance. So I know that my net force, even though my net force is comprised of forces in the x direction, so F net x, and forces in the y direction, F net y, I know that my forces in the y direction, well, they balance to 0. So that's gone. So that means that my acceleration, which as I would expect, if I'm pulling on the block like this, it's going to move in this direction, right? So it's moving in the x direction. That's the direction of the velocity and thus the acceleration. Okay, so F net x equals ma. Remember that F net x, this is the same thing, so it's equivalent to sum of the forces in the x direction. These two things mean the same thing. So just make sure you're comfortable looking at it with either types of symbols. So that's equal to ma. So I have two forces in the x direction, tension and force of friction. Tension's in the positive x direction, force of friction's in the negative x direction. So I'm going to replace the left side of these equal signs with T minus FF. That's equal to ma. T is 50 newtons, FF is 30 newtons. That's equal to 25 kilograms times acceleration. 50 minus 30 is 20. 20 equals 25a. Okay, so acceleration is 20 divided by 25. If you divide the numerator by 5, you get 4. Divide the denominator by 5, you get 5. 4 divided by 5 is 0.8. So acceleration is 0.8. That's meters per second squared. Okay, so that is the acceleration. Now, that is the magnitude of the acceleration. We can stick a little direction in here too. So let me just force that into a square bracket. The acceleration is going to be, well, since it's positive, that means it's going in the positive x direction. Hence, it's going in the direction of tension. It's going to the right. So there we go. There's our complete final answer. Excuse me. Okay, let's go back to the slides. And we'll just make sure. Yeah, there we go, 0.8. Okay. Use F equals ma to show that the formula for weight is correct. If you remember, we actually did this in the previous video. We showed that using the formula F equals ma, if the only force acting on the body is gravity, so for example, in the case of projectile motion, then F would become W, and the acceleration is that due to gravity, which is lowercase g. Right? So there's Wile E. Coyote falling off the cliff. All right, so A is the free fall acceleration or acceleration due to gravity, hence W equals mg. And this is the formula that we just accept. Remember that it's not on your formula sheets. You have to remember this or be able to obtain it looking at this and understanding where it comes from. Okay, next, a 1,000-kilogram airplane. So there's that airplane again that we finished off with last time, is flying in a perfectly level flight. The drag, capital D, is 25,000 newtons and the thrust F is 40,000 newtons. Find its acceleration. All right, so again, I hope you have the slides in front of you, so you have the question in front of you. So every time I go back and forth between the slides and my sheet, you're able to see the question. All right, so here we go. So we had a plane. Okay, so something like this. And we have the wings. All right, so you've got your airplane. It's a 1,000-kilogram airplane. That's really light. Okay, that's 1,000 kilograms is a metric ton. And yes, there are different types of tons. There's a metric ton and then there's the imperial ton. So metric ton is 1,000 kilograms. There used to be cars that would weigh 1,000 kilograms. All right, so it's not unusual. All right, so 1,000-kilogram airplane. Drag force, so that's going, drag is going opposite the direction of flight. So there's drag, there's your thrust, your weight, and lift. This time I'm just drawing the forces all coming out of the center. Drag force is 25,000 newtons. let's see, thrust. Oh, this time thrust is 40,000 newtons. So this plane is accelerating. It's not traveling at constant velocity like before. So if I wanted to make this a bit more accurate, I could actually draw this F arrow a little bit longer. Okay, but since I've already drawn it in, I'll just leave it in for now. Find its acceleration. So acceleration comes from net force. Okay, so, excuse me, Newton's second law tells us that F net equals ma. So acceleration is F net divided by mass. So looking at this problem, I have to define my positive directions yet again. You always need to do this. If you have a problem with A, B, C, you don't really have to keep doing that for each part. But if it's a new question, you have to keep doing this again. Okay, so, oh, sorry, F net divided by mass, not divided by x. Okay, all right, so net force comes from the x and the y directions. But just like before, because this airplane is not accelerating up or down, we know that the lift and the weight force are going to balance each other. And we're actually specifically told that in the problem too, that it's flying in perfectly level flight. So that means we only really care about the forces in the x direction. So F net is really F net x, and acceleration is really acceleration x. After all, it's accelerating in the x direction, right? So let's solve that over here. So AX is equal to F net x over m. So that's going to be F minus D for F net x divided by m. F and D are given to us, so 40,000 minus 25,000 divided by 1,000. All right, 40,000 minus 25,000, that's 15,000 divided by 1,000. All right, now I'm going to show you a trick in case you've never seen this before. If you have a number with a lot of zeros on the top and the bottom, what you can do is this, cancel out 1 for 1. So 1 0 from the bottom for 1 0 on the top. Next, cancel those and those, and what are you left with? 15 over 1. Okay, that's what you would expect, 15,000 divided by 1,000. How many thousands go into 15,000? Well, 15 of them. All right, so 15, the units for acceleration, meters per second squared. The direction that it's going, you could call that forward. I know in the original slides, they use the direction right, which also could work here, but I think forward makes a bit more sense. So there we go. Let's go back to the slides. Excuse me. Okay. Now this is similar to what we saw in the previous video. It's not exactly the same, but it's almost exactly the same. We have a 25 kilogram object with exactly two forces acting on it, 40 newtons and 30 newtons, and they're applied simultaneously to it. What is the object's acceleration? Now, like I explained in the previous video, this is not a true example because we're ignoring forces of gravity here. That's really important too. Right? And in this calculation, they don't take into account force of gravity. Right? So it's a little off-putting, I guess. Give me 1 second, guys, because let me just double check if they take that into account. In reality, you need to be taking into account force of gravity, but I don't want to say something different than what's in the slides. Let's see here. F net X, F net Y. Yeah, they're ignoring gravity, unfortunately. Okay. So you know what I'll do? I will actually solve this the correct way. Okay, so that means my solution is going to have a different answer than the answer on the slide. So just make sure you understand that. I hope you don't look at the slides later, forget what I just said now in the video. Okay, so the answer I'm going to get is different than the answer you're going to see in the slides, because I'm not going to ignore gravity. I'm going to keep it a real problem. Okay, so let's go back to the page. Well, you have that question in front of you. All right, so we've got our box. When you do problems for me, okay, when you do the homework, or if you do a live evaluation or a task or something realistic, you will always include gravity if it exists, unless the question specifically tells you not to. Excuse me. Okay, that's F1 and 25 degrees. That's 40 newtons, and this one is 30 newtons. Okay, so we have those two forces that are given to us, but you know that there is another force acting in this system too. It's called gravity. Okay, and gravity, also called weight, that's going straight down. Now, I guess the reason why they may not have included it in this problem is, well, this is a 25 kilogram object. I mean, is it sitting on a table? Is it floating through the air? It's really hard to figure that out at the moment. Because we're not told that it's on a surface, you cannot assume it's on a surface, and it's certainly not in the picture, which is why I didn't include a normal force. But I'm going to include the weight force. So this might just be a snapshot of one point in time where there are these two forces applied with ropes or chains on the object, and of course the weight must exist as well. Okay, so mass is 25 kilograms. So as usual, I have to define my positive x and y directions. It's a new problem. X is to the right positive, y is positive up. And I take my F1 force and I break it up into its components. So I'm going to break it up into a horizontal x and a vertical y. So I have F1y and I have F1x. And of course, those meet at 90 degrees to each other. All right. Now, when I want to calculate the goal of this question is to find acceleration. I have mass, and I know that I'm going to find acceleration by using the sum of the forces is equal to ma. Now, I'm writing it a bit differently this time to get you used to it. In the first problem, when I used Newton's second law, I wrote it as F net equals ma. So I can write it like that. I can also write it like this because, again, sigma F and F net mean the same thing. Okay, so m times a, I can find a because I have m. I just have to calculate what the net force is. And this is essentially what we were doing in the previous video. Okay, so sum of the forces, this is a combination of sum of the forces in the x direction plus sum of the forces in the y direction. So we have to account for both. All right. Now, in the x direction, so sum of the forces in the x direction is equal to mass times acceleration in the x direction. So sum of the forces in the x, oh, I only have one force in the x, it's F1x. So actually, you know what, I don't need to do this part. I'm going to find out the sum of the forces not by multiplying m times ax because I don't know what ax is. I'm going to look at the forces individually. So sum of the forces in the x, that's just F1x. Okay. F1x is F1 cosine of 25 degrees. So F1 cosine 25 degrees. And F1 is 40 newtons, so that's 40 cosine 25 degrees. Okay, so here we go. 40 times cosine 25. And we get 36.3. That's 36.3 newtons. So that's sigma F sub x. Okay, let's find the sum of the forces in the y direction too. So y direction. So sigma Fy, well, looking at the picture, I have 1, 2, 3 forces in the y. F2, F1y, and W. Now, F2 and F1y are both in the positive y direction, and W is in the negative y direction. So that means I'm going to have F2 plus F1y minus W. And that's, I'm trying to figure out the right side of this formula, right? So F2 is 30, and that's just based on the problem. F1y is going to be 40 times sine 25 degrees. And weight, remember that W is equal to m times g, right? So what's mass? It's 25. So minus 25, and g is acceleration due to gravity, 9.81. By the way, if some of you are looking at this and wondering, how come she's not putting a minus sign in front of the 9.81? The reason is, remember what the minus sign is there for in the first place. The minus sign is telling us that acceleration due to gravity is going down. And that's fine because I defined up to be positive, so down would be negative. But I already compensated for the fact that gravity is going down by putting a minus sign in front of the force. So by already compensating for it here, I don't put another negative here because then those two would, well, I guess it's like the expression goes, it's a double negative. So it outdoes what I was trying to do originally. All right, so here we go. I've got 30 plus 40 sine 25 minus 25 times 9.81. So I have minus 198.3. Okay, so the fact that I'm getting a negative force means that it's going down. The majority of the force is going down. Okay, so sum of the forces in the y direction. Okay, now the next step, at this point, I have to combine these two. I have one sum in the x, one sum in the y. So in my x direction, well, it's pretty small, 36.3, and I have a huge force in the y direction going down. So this is 36.3, and this is minus 198.3. And the sum vector is going to go from the tail of the first vector to the tip of the final vector. So like that. Okay, so this is actually the sum of the forces. That's 90 degrees, and this will be my angle. All right, so the magnitude of the sum of the forces is equal to, using Pythagorean theorem, the sum of the forces in the x magnitude squared plus the magnitude of the sum of the forces in the y direction squared. So notice this part's exactly the same, except instead of the sum of the forces being equal, well, to balance, it's going to be equal to mass times acceleration instead of 0. All right, so that's going to be 36.3 squared plus its magnitude. The magnitude of negative 198.3 is 198.3. Right? So just the, without the negative sign, 36.3 squared plus 198.3 squared. Square root 200, and let's just call that 202. Okay, 202 newtons. That is the magnitude and the angle for the direction we get using the angle. So theta is equal to the inverse tangent of the magnitude of the sum of the forces in the y over the sum of the forces in the x. Okay, so that's inverse tangent of, okay, since it's magnitude, you're putting 198.3, not minus 198. 36.3. So inverse tangent of 198.3 over 36.3. And by the way, you can put the fraction symbol or the division symbol here. It doesn't matter. It's the same. Theta is equal to 79.6 degrees, which we'll just call that 80 degrees since it seems like we're sticking with whole numbers. So I've got the force, I've got the direction. Therefore, oh, I got to find acceleration, don't I? Okay, easy. Acceleration is sum of the forces divided by mass. Right? We're just rearranging this formula right here. So that's going to be 202 newtons divided by 25 kilograms. Notice if I solve it like this, the units for acceleration are going to come out to be newtons per kilogram. And we saw in the last video that that is also an acceptable unit for acceleration, just as is meters per second squared. So acceleration, let's just call that 8.1 meters per second squared. Ah, there we go. Now the nice thing is, whatever direction your force is, that's going to be your direction for acceleration. So as some people would say it, the net force inherits its direction from acceleration and vice versa, since this is a vector and this is a vector. Mass, on the other hand, as you know, is measured in kilograms, and it is a scalar quantity. So no direction contribution there. All right, so that means the direction for acceleration is the same as what we just calculated for force, which is perfect. So let's see if I can squeeze the therefore statement. Oh gosh, sorry guys, I know this is a little crowded. I'll take out a new sheet for the next problem. Therefore, acceleration is 8.1 meters per second squared, and the direction is 80 degrees at 80 degrees below the horizontal. Okay, so there is our problem solved. So remember, this number and this direction is not going to match what you have on the slides, because unfortunately in the slides they are ignoring the weight. But you have to include the weight. I mean, the object has a non-negligible mass, so it has to be there. All right, so that's why this number will not match up with what's here. Okay, next. We have a 25 kilogram object resting on a frictionless incline, which is released, as shown. What is its acceleration? So in case you missed that little animation, let me just do that again. Okay, so this thing starts from rest and starts sliding down. Okay, what is its acceleration? Now, something that we saw earlier is that when something is speeding up, if you were to take snapshots of it in equal intervals of time, you would see that the distance between it would, well, between each snapshot keeps increasing, and that's just because it's speeding up. Right, so you can see that clearly here. The distance between each successive snapshot is getting bigger. Now, when we draw the free body diagram for the object on the incline, we usually draw it somewhere in the middle. Right, so usually we pick that box. Now, I'm going to go to my page here. We're going to solve this. Oh, we're going to solve it on the page. you need to become familiar and comfortable with solving problems when objects are on inclines, because this is a very popular type of problem in physics. And you're not just going to see this in grade 11, it's going to come back and visit you in grade 12 as well. So 30 degrees, this thing is 6 meters tall. And we're going to assume that the block is right here. Okay. So at some point in its path, mass is 25 kilograms. It's frictionless, so I mean that's going to help us, but the incline won't always be frictionless, so keep that in mind. We're just lucky this time. It's going to be a little bit simpler than it normally would be. Okay, we have to draw the forces acting on this object. Well, because it's made of mass, there will automatically be a force of gravity acting on it, and that force starts in the center of the object and always goes straight down. So this is W. This is my weight. Because the box is on the surface, there is a reaction force from the incline pushing back up on the box because its weight is pushing down on it. Now, in the previous video, I told you be very careful. While the normal force does sometimes point opposite to the weight and sometimes is equal to its magnitude, it is often not. The way to remember how to draw the normal force is that it's a reactive force. And actually, even in the word normal, normal means at 90 degrees. It means perpendicular. Perpendicular to what? Perpendicular to the surface. So my normal force is like this. Okay, so that's N. For questions where you are dealing with an object on an incline, we always rotate our coordinate system. So instead of having a coordinate system where I say X is to the right and Y is up, we abandon this coordinate system and for a new one. Okay, our new coordinate system is going to look something like this. It looks like the original one, just rotated. Okay, so this is going to be positive Y, positive X. Okay, so what are these directions? Positive X is going down the ramp. Positive Y is up and perpendicular from the ramp. So positive Y is the direction of N, positive X is the direction that it's going. You always got to set up your coordinate system like this if you want to make it easier to solve this kind of a problem. All right, now whenever we have forces in a problem that do not line up with our coordinate system, we have to resolve it into its components. So in this case, the normal does line up with our coordinate system. It's in the positive Y direction, but weight does not follow either of these coordinate directions. So we have to resolve it into X and Y components. Remember that whatever vector you're trying to resolve, it represents the hypotenuse of a right angle triangle. And so the legs of that right angle triangle have to be in these directions. Okay, so what that means is I'm going to have my Y component of weight like that and my X component of weight like that. So X is going down and to the right, Y is going down and to the left. Okay, so and those both meet at 90 degrees, so that's weight Y, and this down here is weight X. Okay. So that means in total now I have two forces in the Y direction, N and WY, except they're going in opposite directions. And I have one force in the X direction, that's WX. Right, now, there's one more piece of information that you're going to have to remember. In addition to remembering that you're always going to have a rotated coordinate system, you have to remember this angle in here. Okay, so there's that triangle, so the angle between WY and W. Whatever the angle to the incline is, so in this case it's 30 degrees to the horizontal, this angle will always be the same. Okay, so some simple trigonometry will show you that that is the case. If you're interested to see how that is, just send me an email and I will show you. Okay, but this angle and that angle are always the same. So what that means is, and I want to just draw this again because it's getting a little bit crowded in this picture. So usually the way I like to do it is, even though the normal force is coming between these two surfaces, it's coming from the incline rather, I like to draw the normal force coming from the middle. It just makes it easier to solve these kinds of problems. So we have weight, we have normal, and then weight we break down into Y and X. So weight X, weight Y, and that's 30 degrees. I hope that's a little bit easier to see, okay? And we're still dealing with this coordinate system, of course. Okay. Right, so what are we looking for? All right, we're looking for acceleration. Acceleration. And honestly, most often than not, if you're ever looking for acceleration in a problem, that means you're using Newton's second law. So that means you're looking at the sum of the forces divided by the mass of the object. Okay, so you can call it sum of the forces or you can call it F net. They both mean the same thing. Now for this object, I mean, you saw the animation as it slid down the ramp. Okay, so it's not accelerating up and down on the ramp. It's not accelerating in the y direction. It's accelerating down the ramp in the x direction. That means the acceleration that we're looking for is in reality a sub x, since a sub y equals 0. Okay, so since we're looking for a sub x, that means we're looking for F net x, or the sum of the forces in the x direction. All right. Now, in the x direction, I only have the one force, Wx. Okay, so that's the only force. So acceleration is going to be equal to Wx divided by m, and Wx is W sine 30 degrees. And dividing that by m, now W is equal to mg sine 30 divided by m. Notice I have mass in the numerator and denominator. Product are in quotient, so this cancels. So g sine 30 degrees. And this is actually an important outcome of this problem I want to really emphasize, and that is that when solving physics problems, try not to plug in numbers until the end, because a lot of times you're going to have things canceling out. And a lot of questions actually will not even have numbers to deal with, so you anyways have to get used to that. G sine 30, so that's 9.81 times sine 30 degrees. So that's 4.905. Okay, 4.905, and that's acceleration, so it's meters per second squared. Okay, that's its acceleration. And the direction, well, we can just say down the ramp for now. So let's go back to the slides. Okay. Oh, notice in the slides, they're just approximating it as 5, so that's fine. It's 4.905 rounded up. All right. So same question, what is its speed at the bottom? Okay, so obviously when it gets to the bottom, it's going to have sped up. So let's go back here. So now when it's down here, we want to know what v is. All right, so looking at the problem initially, when this thing is at the top, it's released from rest, right? So u equals 0. We want to know the speed when it reaches the bottom, so we're looking for v. I know that it's undergoing some kind of displacement here, s, and throughout that, it's accelerating, right? It's speeding up, otherwise the speed wouldn't change. I just found the acceleration. The acceleration's magnitude was 4.905 meters per second squared. So I almost have everything I need to use one of my kinematics formulas. If I can find s, I'm pretty much home free. So let's figure out how to find s. Well, if we look at the original problem, the original picture presents us with this kind of triangle. I have my 30-degree angle here, and I have a 6-meter height here. So how can I possibly find this side of the triangle, which is s? Well, it's a right triangle, so to solve a right triangle, I usually use SOHCAHTOA. All right, so with this angle, I have the opposite side and the hypotenuse. And I know that sine of theta, or sine of 30 degrees, is going to be opposite 6 meters divided by hypotenuse, which is s. So that means s is equal to 6 meters divided by sine of 30 degrees. 6 divided by sine 30, and we get 12. So 12 meters. That is the distance that the block gets displaced. Okay, so we have that. So let's write everything neatly. What we have: u equals 0, a equals 4.905. Keep in mind that in the slides it's using 5, so the number is going to come out a bit different. S equals 12 meters, and we're looking for v. In case you forgot the formulas, I really hope you memorized it at this point, but here it is in 2.1. We're going to be using this formula here. V squared equals u squared plus 2as. So v squared equals u squared plus 2as. Sorry, u is 0, 0 squared is 0. So that means V is equal to the square root of 2AS. So square root of 2 times 4.905 times 12. Okay, 2 times 4.905 times 12, square root. That's about, oh, let's just call that 11 meters per second. In your live evaluations, by the way, you're going to be told, whether it's a live evaluation or a test, same idea. You'll most likely be told in the question how many decimal places to give it to, or whether to round it to the nearest whole number, whatever the case is. If it doesn't specify, IB students would be rounding it to the correct number of sig figs. Non-IB students round it to an appropriate number of decimal places, or in this case, whole number. All right, so the speed at the bottom is 11 meters per second. So back here, and yeah, 11 meters per second. Okay, that's good. All right, now we're going to start talking about friction. I mentioned in the last video that we would really start getting into friction in this video. So here we go. Friction is when you have two solid objects that are moving against one another and there is resistance. Usually friction results in the production of thermal energy and heat. Right? So on a very cold day, if you're standing outside and you don't have mittens on, a lot of people, if they don't have pockets, they start rubbing their hands together vigorously. And the reason for that is that's friction. Right? So the two solid surfaces of your hands rubbing against one another produces heat, right? So to keep your hands warm. Now, friction is always parallel to the contact surface and always acts opposite to the direction of motion. Let's just see for a second what is meant by that. What does it mean for friction to act opposite the direction of motion? Well, if you have, let's say you have a box sitting on the floor and there's a rope attached to the box and someone pulls on that rope, well, where would the resistance be? The resistance would be going in the other direction. If there was no resistance, you would pull the box very easily with your applied force of, let's say, 50 newtons. But if there is a resistance, that 50 newtons you're applying might feel more like 30 newtons or 35 newtons. It wouldn't feel as much because there's something pulling back. It feels like there's something just not allowing you to move forward at the rate that you should be able to. So friction is always opposite the direction of motion and parallel to the contact surface. Okay, now imagine you have this crate sitting on the floor and you have this rope attached to it. We're going to pull the crate to the right, gradually increasing the applied force, and we're going to inspect what happens with the friction force. Actually, just before I do that, I want to just go back here for a moment. This is actually a nice experiment you can just try at home so you can understand what's happening with friction. I'm going to grab my cell phone and I'm going to move this page for a second. I mean, I think you should get the gist of it by me showing you this. Okay, so the reason I picked the cell phone is because it's pretty heavy and it fits in the field of view of the webcam. So if I take my fingers and if I apply a force, right now I'm applying a force onto it. I'm not just touching it. It's not moving though, right? So if I push a little bit more, it starts to move. But you can easily rest your finger on this and it won't move because there is some kind of resistive force acting back on you. So even though you apply a force forward, as small as it is, I mean, it's hard not to move it actually because the cell phone's not as heavy as I thought it was, but as much as you want. So you apply a very, very little force there. There is a little force pointing back. So in the region between the bottom of the cell phone and the table, there is a resistive force. In fact, that resistive force is probably more pronounced if I hold the phone like this, right? Because now I've got the rubber. So if I push on the phone like that, it's not going anywhere. And you can clearly see I'm applying a force because my finger is moving, well, it keeps touching it, right? Nothing's happening. That means throughout the entire time that I'm applying a force, there is a friction force resisting the motion, acting in the opposite direction. So moving like that, okay? All right. Now, at some point, if you apply enough force, obviously the phone will start to slide, right? And when that happens, that means you have broken that static friction barrier. So we'll talk all about that in the animation. All right, so we have this crate. There's a rope attached to it, and we're going to plot the force as a function of time that we apply on the crate. Okay, tension will be represented by a green circle, friction by a red hollow circle. Okay, so initially there's no tension and therefore there's no friction. Remember, friction's acting between the bottom of the crate and the table surface. Now we start to apply a little bit of tension force. The block is not moving. So what happens? There's what's called static friction. If you remember in grade 9 science, you learned about something called static electricity. The word static means not moving. Okay, so when an object is not moving, but it still experiences resistance, that's called static friction. Okay, imagine you're sitting in a chair. Okay? If you have a 2-year-old niece or nephew come and try to push the chair, they might apply a lot of force, but there's no way they're going to move you sitting on the chair. You're just too massive. But they're still applying a force. That means there's some kind of resistance there between the bottom wheels of the chair or the bottom legs of the chair and the ground. Okay, so however much tension force is being applied, there is an equal amount of static friction being applied in the opposite direction. So if we were to plot it, it looks like this. By the way, don't pay any mind to the fact that they're not exactly centered. It's done that so that you can see that there's two distinct circles there, but they are in fact the same magnitude. Okay, now we decide to increase the force again. What happens? The object still didn't move. That means the static friction force increased to match the applied tension force. So it increased. Well, it's still not moving, so let's increase the force again. Okay, well, guess what? It's still not moving, but the friction force increased along with it. Okay, so there's our next point. Okay, let's apply a lot of force. Well, it's still not moving, but notice that the static friction force matched the applied tension force. And so here's our next point. Now, something interesting about this point, and for every object, this point will occur at a different, location. For this particular crate, if we apply even 0.1 newtons more force in the tension, we will no longer have this object be stationary. It will start to move. Okay, so hang on a second. See if I can get the animation to work. Unfortunately, the animation didn't work. Sorry, guys. But if we do apply a little bit more force, and by the way, you'll be able to see the animations when I post the completed slides and you download it for yourself. If you were to apply just a little bit more force, that object is going to just slide away. Because at that point, you've broken the attractive bond between the bottom surface of the object on top and the top surface of the object on the bottom. And so what happens after that is you have something called dynamic friction. In some textbooks, this is called kinetic friction. Okay, kinetic and dynamic, they both mean the same thing. It means object in motion. So this object starts to move. So we now apply a constant tension force and there is a constant frictional force. But what's interesting to note is that this dynamic friction force, in other words, the resistance between the objects while they're in motion, is significantly less than the maximum static friction. Right? So static friction kept increasing with applied force, exactly matching it at every turn until we hit the maximum. As soon as we applied a bit more than the maximum, the bond broke free and the object started moving at constant velocity. Okay, and so therefore the friction remained constant, but it decreased. Okay, so we're going to see all of that information here. So static friction force, Fs, exactly matches the applied tension force. Now what's really important is that it increases linearly, and that's just because it equals the applied force until it reaches the maximum Fs max. Now personally for me, I don't just call the force of friction Fs or Fs max. I like to put F subscript F for force of friction, and then I'll put another subscript S for static or D for dynamic. Okay, and then unfortunately if you have Fs max, then you have FFS max, 3 subscripts, but I mean, you get used to it. Okay, dynamic friction, also known as kinetic friction, is F subscript D, and actually what's really interesting is right after you break that bond, the friction almost instantaneously decreases to a lower value, and it sticks with that constant value. So no matter how hard or how fast or however much I pull on this crate now, however much I pull on the rope which drags the crate, the friction force remains constant. So it doesn't matter how fast I pull it. The only thing that would change the friction force is if suddenly the box weighed more or I changed the surfaces. Or technically the box could weigh less too. All right, take note of the following general properties of the friction force. All right, so interesting. So static friction is always between 0 and the maximum. We can see that here. So this is the region of the graph where we have static friction, the maximum being up here, the minimum being here. Okay. Dynamic friction is always less than the maximum static friction. What this really represents is that it's harder to make something start moving than to keep it moving. Okay, next time when you're at home, if you have a dining table or just something heavy that you can push without injuring yourself, so be careful when you do this. Try moving, let's say, your dining table. Okay, it's going to be heavy, right? Imagine, like, try yourself putting a little bit of force on it so that it doesn't move, and then just keep increasing your force and observe that it keeps not moving. So as you keep increasing the force that you're pushing with your hands, the friction force between the bottom legs of the table and the kitchen floor, it's applying a resistive force back. So that's why it doesn't move. And this static frictional force continues to match your applied force until you push so hard that you break the bond between the bottom legs of the table and the top surface of the floor, and the table breaks free. And so at that point, you're going to notice that it's a lot easier to move the table than it was to get the table moving in the first place. That's what this graph really represents, and that's what this little middle expression represents. And the last thing is that dynamic friction is constant, and I just talked about that as well. You can increase your speed, decrease your speed, but friction will be constant. Okay. So what causes friction? Well, if any of you know anything about polishing metals, there's a concept in, I guess, manufacturing called welding. I'm sure you guys know what welding is. Welding is you have to put on a special mask because there's a lot of bright light given off when a person welds. Welding essentially means you take two pieces of metal and you expose one to such a high temperature that it essentially melts at that location. And you can, I guess, merge that. You can attach it onto another piece of metal. Okay, so when you attach two pieces of metal, you have effectively welded them together. But usually when people think of welding, they think of heat, which makes sense. I mean, you have to make one metal melt and attach it to the other metal. If you make both of them melt and attach them, even better. But you might be surprised to learn that there is something known as cold welding. And you can make two pieces of metal stick together in a cold environment too, just as if they were hot. And in fact, the cold might stick together better. And that might be really surprising to you. Okay, so how do you make two cold metal surfaces stick together? Well, the cold metal surfaces have to be so smooth. In other words, they need to be polished to such an extent that when they're brought close together, they actually just stick. And in a lot of cases, it is almost impossible to separate them. So effectively what's happening when two surfaces are, well, on top of each other, it's almost like they're cold welding. Okay, so in reality, when you look at a surface, not when you're looking with your eyes, but if you were to look through a microscope, you would see these imperfections. You would see these hills and valleys on top of each surface. It's not smooth. Even a piece of paper, it looks something like this on top. It's not smooth, especially if you were to use a very, very strong microscope. Right? So when you put these two surfaces on top of each other, there are various spots and locations where the hills and valleys, they grab onto each other. So let me just show you something with my hands. Right? So if you have, for example, a hill and you have a valley, they can grab onto each other. So let me show you like this. So they can't move across each other, right? So because there's friction. Now, if I apply enough force, I can break free of that and just move my hands across. But if it's not a lot of force, these two hills and valleys will hit each other and they cannot move across one another. Okay. So essentially, one way to look at this is that the two surfaces have cold welded together. And so if you try to move them across one another, the cold welding opposes the motion until you apply enough force that it's actually able to break free and then move at its constant velocity. Another way to look at it, let me actually just take out that last point. Another way to look at it is that these hills and valleys get caught on one another. Right? So just like if you have two sets of teeth moving across each other, they're going to keep grabbing each other at various parts, just like I showed you with my fingers. Right? So, but if you move it fast enough, you can break free of those bonds and those attractions. Now, friction varies. If you are trying to move, a piece of rubber, excuse me, across a piece of sandpaper, it would be difficult. because the rubber and the sandpaper together produce two very rough surfaces and would make a lot of friction. But if you try to move an ice cube across a piece of linoleum or plastic or marble, it would be very easy because the coefficient of friction between those two materials would be very small. Okay, so what is this coefficient of friction? It's a value that we use to describe, hang on one sec, sorry. It's a value we use to describe how rough two surfaces are with respect to one another. In reality, this coefficient of friction, which is symbolized by the letter mu, let me go back to the page here for a second. Okay, so this is the Greek letter mu, and we use it for a coefficient of friction. Now you've seen that you've seen that symbol before, except it didn't stand for coefficient of friction. It was in your data booklet. So let's see if we can find it. In your data booklet at the beginning under metric multipliers, right, just as you know that kilo represents times 1,000, mega times a million, there's all sorts of prefixes here. There was a prefix called micro, and micro is also represented with the symbol mu. Okay, so there it is. It's times 10 to the minus 6. Just wanted to show you guys that so you don't get confused later on. But that mu is a prefix. The mu here, this is an actual quantity that you're going to see in the equations. Now, this is a unitless quantity. The reason why it has no units is because it is the ratio of the force of friction to the reactive force, or the normal force, as it's shown here. Now, because there's two types of friction, you have static friction and you have dynamic friction, it therefore makes sense to have two types of coefficients of friction: static coefficient of friction and dynamic coefficient of friction. And like I mentioned, the values of these coefficients tell us how smooth or rough the surface is. Okay, so the larger the value of the coefficient, the more rough the surface is. And the smaller the value, the smoother the surface is. So generally speaking, mu(s), the coefficient of static friction, is always going to be greater than that of dynamic friction between the same two surfaces. And so we come down to these two formulas. These are the last two formulas on your formula sheet in box 2.2. Okay, so force of static friction, it's always going to be less than or equal to mu(s) times r. I just want to talk about that for a moment. Why less than or equal to? Okay, so why for dynamic friction, the force of friction is equal to the product of the coefficient of friction and the normal force, or the reactive force. But for static friction, it's less than or equal to. Well, the reason for that is based on the graph. Just as when I told you, pretend you're pushing your dining room table. If you apply a little bit of force, so let's say you apply 5 newtons of force, the table doesn't move. That means there is a 5 newtons of static friction force pointing back at you. If you apply, excuse me, if you apply 7 newtons of force and the table still doesn't move, that means the table is able to apply 7 newtons of force back at you. There's a 7 newtons of frictional force. If then you up it to 8 newtons of force and the table begins to move, that means you have just supplied the minimum force required to break free of that cold welded bond between the atoms of the bottom of the table legs and the top of the floor. So the maximum static friction that you can have is equal to mu(s) times r, whereas every other amount of static friction is going to be a number between 0 and that maximum. Excuse me. All right, let's try this problem. A piece of wood with a coin on it is raised on one end until the coin just begins to slip. The angle the wood makes with the horizontal is 15 degrees. What is the coefficient of static friction? Okay, I am going to attempt to demonstrate this with a book and a ruler, so give me one moment. Okay. So I'm going to go to my camera here. Now this is, by the way, a really nice book, The Simpsons and Their Mathematical Secrets. I don't know how many of you watch The Simpsons. It is one of the top TV shows. It is a cartoon, very long running. And there's actually a lot of mathematics in this book. This is a really nice book by Simon Singh. If any of you are interested in mathematics, there's actually very high level mathematics. In fact, the writers of The Simpsons, most of them have their masters and PhDs in physics and mathematics. So if you watch the show, there's actually a lot of hidden high level mathematics in it. It's quite astonishing when you actually see it. But anyways, I'm getting off track here. I have a book which I'm going to create into an incline. I'm going to do that by raising it. So I know it's a little bit hard to see from the angle of the webcam, but that's what I'm doing. I'm keeping this side of the book constant on the table, and I'm raising the spine. Okay, so what I'm going to do is I'm going to take my little triangular ruler and I'm going to rest it here, and slowly I'm going to raise the angle. Okay, so keep in mind that the angle here that I'm measuring is the angle between the book and the table. And so this angle is essentially going up like this, right? So I'm going to increase the incline until this thing slides down. Give me 1 second, everyone. I apologize. My allergies are really, really bad. Excuse me. Okay, so I've got the ruler on the, let's call it on the incline, and I'm going to start raising the book. Okay, so I have raised it up at some angle now, but the ruler hasn't started moving yet. So I'm just going to keep raising it. Notice the ruler still hasn't moved. I'm going to keep raising it. The ruler still hasn't moved. It will move soon though. Still didn't move. There's a lot of static friction holding it in place. There we go. So if I was to hold this book exactly where I have it and measure the angle, I would be able to figure out actually the coefficient of static friction. What is the coefficient of static friction between the surface of the book and the surface of the ruler? I could actually calculate that. Okay, so that is what's happening here. All right, let's go back to these slides for a moment. Okay, so here we have a piece of wood with a coin, but it's the same idea as having the book and the ruler. Okay, so you just keep increasing the incline until the coin slides and falls. And unfortunately, the animation doesn't seem to be working. I think it's probably the amount of RAM I have. The computer's a bit slow right now. Okay, so we can see based on the question that the angle the wood makes with the horizontal is 15 degrees once this thing starts to slide. What is the coefficient of static friction? But you know what? I'm going to show you something a bit more interesting than that. I'm going to show you, well, what if you didn't know what the angle was? What if you just wanted to figure out the coefficient of static friction given some arbitrary angle? Okay, so you don't actually know what the value is. You're just trying to figure out what it could possibly be. We will solve it like that first, and then we'll plug in theta is equal to 15 degrees. So this is going to show you how one can always determine the coefficient of static friction. Okay, so example, and I have my horizontal, and I have my incline. So this is essentially the piece of wood, and then this would be the coin. Now in this case, I am going to include the force of friction, of course, because as I was raising the book with the ruler on top, well, the ruler didn't fall, right? It didn't fall until I raised it to a particular height, then it started to slide off. So that's when I finally breached the maximum static friction. So the first thing I'm going to do is draw all of my forces. Because this box or this coin, or let it be a ruler, it has weight, I'm going to draw the weight force going straight down. It's on a surface, therefore there is a normal reactive force, and that is perpendicular to the surface, so it's going to go like this. This object, whatever it is, it wants to slide down the ramp. So that means there's going to be a friction resistive force up the ramp. Now, let's say at this point it hasn't slid down the ramp yet. It's actually being held in place. So at any point in time while I was raising the book and the ruler stayed where it was, we had a frictional force. In fact, it was a static frictional force, so FFS. Okay, if you want to just call it FS, that's fine. Imagine we are looking at the point where we just prevented it from slipping, just prevented the ruler from slipping down the book. Okay, that would be the maximum static friction, FFS max. Okay, now that is the only way we can calculate the coefficient of static friction, by using the maximum static frictional force. All right, so remember that I said for questions with an incline, and okay, let's say this is inclined at theta, right? Because I said let's not actually make a specific value this time. For questions that are on an incline, you are going to change your coordinate system. Because this thing wants to accelerate down, I'm going to let down be my positive x and up be my positive y directions. So like that, okay? So down the ramp, positive x, up and perpendicular to the ramp, positive y. That means that FFS max is in the negative x direction, normal is in the positive y direction, but weight does not fall into either of the categories. So I have to break it down into its x and y components. So here we go. So there's wy and there's wx. And there's theta, right? So remember I said earlier that whatever angle this is relative to the horizontal, it's going to be the same angle in there. Okay, so we are looking for the coefficient of static friction. In order to do that, we are going to inspect Newton's second law from the x and the y directions. So from the x direction, we have sum of the forces is equal to ma. Now, this is acceleration in the x, by the way. In the x direction, if we are considering the point where this object is just about to slide, but it doesn't, that means it's not accelerating. It's technically still at rest. So if acceleration is 0, 0 times any mass is 0. So that means we're looking at 0 sum of the forces in the x. All right, so what forces are in the x direction? Well, I have two of them. I have wx going down in the positive x direction, and I have FFS max going in the negative x direction. Only these two. So that means 0 is equal to wx minus FFS max. Okay, so what that means is I can take FFS max on the left, keep that positive, and then write wx on the right. Now, FFS max, remember the whole point of this is to find the coefficient of friction, or in this case, an expression for the coefficient of friction. So frictional force, in case you forgot, grab your formula sheet. So in box 2.2, we have our formulas. So we have FF is less than or equal to mu s times r, or n, right? N is the normal force, which is also r, the reactive force. It's equal to this when you're dealing with the maximum static friction, which is what we're doing here. Okay, so this is going to be mu s times n on the left, and wx, always rewrite the forces in terms of their original force, the components in terms of their original force. So wx would be w times sine of theta. Now, what is w? W is mg, right? So mg sine theta. Now what we're going to do is try to come up with an expression for n. In fact, watch what I can do. Mu s is equal to mg sine theta divided by n. I'm trying to come up with an expression for a normal force. Since normal force is in the y direction, I'm going to go to the y direction and see if I can come up with a better expression for it. So sum of the forces in the y direction is equal to ma in the y direction. Now, this object is not accelerating up and down the ramp. So acceleration in the y is 0, which means 0 times mass is 0. So 0 is equal to the sum of the forces in the y. In the y direction, I have two forces. I have normal in the positive y, and I have wy in the negative y. So this is equal to n minus wy. So that means n is equal to wy, right? So n is not equal to w, it's equal to wy here. That's why I said normal is not always equal to the weight. Sometimes it's a component of the weight, sometimes it's a component of the weight with another force. You have to work it out by always inspecting the net forces in the y direction. So n is equal to wy, and wy is w times cosine of theta. So that's mg times cosine of theta. So there's my expression for n, and that's going to get plugged in over here, okay? So mu s is equal to mg sine theta over mg cos theta. Well, guess what? mg divided by mg is gone, so I have sine theta divided by cos theta left over. And those of you that remember your trig identities, sine theta divided by cosine theta, that's equal to tan theta. Now, if you didn't know that, you have to remember that. That's super important. Sine theta divided by cos theta is tan theta. But guess what? That's also mu s, right? So that means, therefore, okay, let me write it over here. Therefore, mu s is equal to tan theta. This is a remarkable result. What this means is that no matter what surface you have, what two surfaces you have, what object on top of what kind of surface, whatever angle you get to, and whatever angle it is that makes the object start sliding, if you take the tangent of that angle, you get the coefficient of friction. So that's just remarkable. By the way, when using this formula, theta has to be in degrees. I know that doesn't mean much to you right now, but it will later when you start learning about other ways of expressing angles. Okay, so that is the general conclusion. Always try to remember that, especially how we came to that conclusion. Looking at the net forces in the x, looking at the net forces in the y, and of course the only way we were even able to do that was by drawing the proper free body diagram and the rotated coordinate axes. So having done that, we can go back to the problem and actually answer it now. Okay, so the angle the wood makes with the horizontal is 15 degrees. What is the coefficient of static friction? So therefore the coefficient of static friction is tangent of 15 degrees. And that's it. Now in reality, if this question was asked to you, you can't just say US is equal to tan theta. Why? Because that's not a formula in your book. The only two formulas that are not in your book which you can use are the W is equal to mg and V equals S over T. Okay, so those are the only two. Other than that, you should be deriving the formulas on the spot. Okay, so you would actually have to go through all these steps. But still, it's important for me to show you this. If you were doing a multiple choice test, for instance, obviously showing work doesn't count for multiple choice. So in that case, you could just plug it into this equation fast and get the answer. So we get 0.28. Remember that the coefficients of friction are unitless quantities, and that's because really they're just a ratio of forces. Okay, so 0.28. That's not a very rough surface. Okay. All right, now suppose the plank of wood is long enough so that you can lower it to the point that the coin keeps slipping but no longer accelerates. If this new angle is 12 degrees, what is the coefficient of dynamic friction? Okay, so that's interesting. So we've still got a ramp. Okay, so let's move this up. Let me actually draw this with the black marker. So almost, well, pretty much exactly the same diagram, except I'm going to call this FD. All right, so we've got our angle, and it's 12 degrees now. We've got our object, there's weight, there's normal. This time there's dynamic friction, FFD. Okay, so something like that. Just like before, we are going to set up our coordinate system. So positive x is going down the ramp, positive y is up and perpendicular from the ramp. And we break up w into its y and x components. So wy is going down and wx is going down and to the left. That's 90 degrees, and this angle in here is 12. All right. So because in this situation the coin no longer accelerates, or whatever the object happens to be, that means the velocity is constant. So if the velocity is constant, well, if there's no acceleration, we can just say acceleration is 0. Actually, I think there's a problem on the slides. I think in the slides it says v equals to 0. That is not correct. I will change that and make sure that when the slides get uploaded, it will say a equals 0. Okay, but it's a equals 0, not v equals 0, because v can be constant and you can have a 0 acceleration. Okay. Right. So we are looking for the coefficient of dynamic friction here. So we are once again going to inspect the net forces in the x and the y, just like we did before. Okay, except this time, well, acceleration, well, it's still going to be 0 actually, so that's quite nice. Okay, so if we look at the x direction, we will have, so that we know the sum of the forces is equal to 0 because acceleration is 0. And so that's going to be wx minus ffd equals 0. By the way, if you're wondering why I'm going through all these steps again, it's very good practice for you to get in the habit of solving these types of problems, because a lot of the problems in physics do involve using Newton's second law in the x and y directions based on a free body diagram. So this is excellent practice. Okay, so wx is w sine 12 degrees, and that's equal to ffd. Okay, w is mg, I don't think we're given the mass, but that's okay. I think it's going to cancel out anyways. mg sine 12 degrees. Force of friction dynamic, that's mu d times the normal force. So mu d is equal to mg sine 12 divided by n. Okay, moving on to the y direction. You'll notice that I'm doing this a lot faster because I already did this in the previous problem. So I hope you're able to follow along with that. All right, so that's going to be n minus wy equals to 0, and equals wy, which is equal to w cosine 12 degrees, which is mg cosine 12. In fact, I don't even need to convert the w to the mg. You can probably see that. mg sine 12 divided by mg cosine 12. So same idea, sine over cosine 12 is tangent of 12. If you don't believe me, try it out. Tan 12 is 0.21. Let's call that 0.21. Okay. So mu d equals 0.21. Just like the coefficient of static friction, it is unitless. Oops, there we go. So in the text, in the slides, they've kept one more decimal place, which is fine. Something to notice is that the coefficient of dynamic friction is less than the coefficient of static friction. And that is just a natural consequence of the fact that the force of dynamic friction is, generally speaking, always less than the force of static friction. Okay, here we go. Next, a 100 Newton crate is to be dragged across the floor by an applied force F equals 60 newtons as shown. The coefficients of static and dynamic friction are 0.75 and 0.60 respectively. What is the acceleration of the crate? So this is a common tactic in physics problems. They will give you both coefficients of friction, and there might be multiple parts to the problem. Maybe there's a part where the object isn't moving and then it starts moving, or maybe the object isn't moving the whole time, or maybe it is. And it's up to you to understand which coefficients to use and when. Sometimes there is extra information given in the problem, and sometimes there isn't. So you really got to know what you're doing here. That's what I'm trying to get at. Okay, so let's look at the diagram, the 100 Newton crate. Now, when you're told that a crate is 100 newtons, what that's telling you is that 100 newtons is its weight. So you would take that information and you would use it to find its mass. So if weight is equal to 100 newtons, weight is equal to mass times acceleration due to gravity. Thus, you can find mass. You simply take 100 and divide by 9.81. But that's what it's trying to communicate. A 100 Newton crate is to be dragged across the floor by an applied force of 60 newtons as shown. The coefficients of static and dynamic friction are 0.75 and 0.60 respectively. What is the acceleration of the crate? Okay, so the force is being applied at 30 degrees above the horizontal. So take a moment, copy that into your notebooks. Well, I'm going to do the same. Hopefully you have the slides in front of you, so you have the question in front of you, but let's go ahead and solve this. What is the acceleration? Okay. So here's my crate. Now I have, well, in the picture, let's just draw what they have in the picture first. We have our force of friction, we have our normal force, we have our weight, and we have an applied force, and that's 30 degrees. Let's see, what else are we told? We're told that the weight of the crate is 100 newtons. F is 60 newtons. We're told that µs is 0.75 and mu d is 0.60, and we're looking for A. Okay, so we have this type of free body diagram. What I want to do is redraw this so that all the forces are coming out of, well, one point, because it'll be a lot easier to see which are going in the positive and negative x, y directions. But keep in mind, this is the true accurate free body diagram. So if you're ever asked to just draw a free body diagram to get marks, you would draw this right here. Okay, but for solving the question, it'll be easier if we just work with something like this. Keep them all coming out from a single point. Force of friction and F. Okay, so because we're dealing with x and y directions, I'm going to define my positive coordinate directions. So x positive is to the right, y positive is up. And, well, I mean, we're looking for acceleration. That means we're dealing with Newton's second law. Hopefully you can see that already. Acceleration is the sum of the forces divided by mass. I mean, at the end of the day, that's what I need. And I have forces acting in my x direction and in my y direction. Now, based on the wording of the problem, the question says the 100 Newton crate is to be dragged across the floor. So this thing is getting dragged in this direction. There's the direction of its velocity. This box or this crate is not getting accelerated up and down. It's getting accelerated to the right or forward. So that means that in my y direction, I don't have any acceleration. Therefore, I have no net force. So even though the total forces, it's coming from the x and the y directions, I know that in the y direction, my net force is 0. Okay? So I have to figure out what my net force is in the x direction, which essentially means that my acceleration is really just an x acceleration. So you can label that with x if you choose, but you don't need to. Okay. Now, I have only one force that doesn't fit within my coordinate system, so I'm going to resolve it into its x and y components. So here we go. We have F sub x, and we have F sub y. Those meet at 90 degrees. Okay. So in my x direction, I have F sub x in the positive x direction and F sub f in the negative x direction. Now, if the crate is asked what the acceleration of the crate is, that would imply that it's in motion, which means we're dealing with dynamic friction. Okay, so FFD, FFD. So this is going to be, acceleration is sum of the forces, so Fx minus FFD divided by mass. So F sub x, well, that's just one side of this right angled triangle. I know what the hypotenuse is. I know the hypotenuse is 60. So therefore, Fx is going to be 60 cosine 30 degrees. Now, FFD, the force of dynamic friction is going to be the coefficient of dynamic friction times the normal force. And of course, that gets divided by m. What some people will choose to do is solve for some of the forces separately and then just plug it into this formula. So you don't have to keep writing over m. That's up to you. In order to find the normal force, I'm going to have to investigate the forces in the y direction. So regardless, even if the sum of the forces in the y direction are 0, oftentimes you're going to have to still look at the y direction. So going in line with that, the sum of the forces in the y direction are 0. In the positive direction, I have n and f sub y. And in the negative direction, I have w. All right, so n plus f sub y minus w equals 0. So if I was to isolate for n here, n is equal to, so that's going to be w minus f sub y. W is mg, and f sub y is f sine 30, but f is just 60. So that's going to be 60 sine 30 degrees. All right. You know what, actually, I don't have to change this to mg because I know what the weight is. It's 100. So actually, I can just call this 100. Excuse me. Excuse me. 100 minus 60 times sine 30 degrees. So the normal force is 70 newtons. Now this is going to look kind of weird. N equals 70 N. You just got to understand that this N is the normal force and this N is the newtons. This is why some people decide to use R for reactive force. So up to you. So that gets plugged in over here. And we are looking for acceleration. All right, so mass. Actually, let's do a quick calculation for mass. If weight is 100 newtons, weight is equal to m times g. Therefore, mass is equal to weight divided by g, which is 100 divided by 9.81. Excuse me. That's 10.2 approximately. So about 10.2 kilograms is the mass. So we have 60 cosine 30 degrees minus 0.60, that's the coefficient of dynamic friction, times the normal force, which is 70, divided by mass, which is 10.2. All right, here we go. 60 cosine 30 minus 0.6 times 70 equals, and then divided by 10.2. 0.9766, so 0.98. 0.98 meters per second squared. And that is the acceleration of the crate. And of course, that's taking place in the positive x direction. Or you can call that forward. Both of those are acceptable. Okay, let's go back to the slides. Now something interesting here. Will the crate even move? Okay, so this is an interesting consequence. So we actually went ahead with the notion expecting that the crate was moving because the question did imply that it is accelerating. But when we actually calculate this much closer, the crate actually doesn't even begin to move. So, well, let's see how we could figure that out. Let's go back to the paper for a second. How would we even be able to figure out if the crate was moving? Well, we know that there's going to be some kind of static friction acting on the box, right, between the bottom of the box and the top of the surface of the floor. So we have to see what the net force is, first of all. Now, the net force acting on this block in the x direction is this, right? Well, Fx minus FFD. The only applied force is this Fx, right? So we should actually first calculate what the maximum static friction is going to be. So FFS max. FFS max is equal to mu s times n. Now we already found the normal force. The normal force is 70 newtons. So mu s is 0.75, so that's right here. So 0.75 times 70. So what do we get? 0.75 times 70. 52.5 newtons. So there are 52.5 newtons of force, static friction force, acting on the crate. So that means in order to get the crate moving in the first place, I have to apply more than 52.5 newtons, right? So how much force is actually getting applied? Well, this is the force getting applied, F, right? Specifically in the x direction, it's Fx. So what I care about is how big is Fx? Well, Fx I calculated. Fx is 60 cosine 30. So let's actually formally calculate that out. Fx is equal to 60 cosine 30 degrees. Oops. 60 times cosine 30. So that's 51.96. Now those two are very close, but they're not the same. So I need at least 52.5 newtons to break the static friction barrier, so FFS max, but I'm only applying 51.96 newtons. So actually, the slides are correct. This crate is not actually even moving. Okay, so if I apply this much force in the x direction, that means the static friction force will actually be 51.96 newtons. Okay, so that's quite interesting. Actually, let me just come back here for 1 second. If the crate is already in motion, so we're not trying to break it free of its static attraction to the ground. If it's already in motion and you're applying this force, this would be the correct solution and this would be the correct acceleration. But since, yes, we do not technically know whether it's moving or not, we have to inspect the magnitude of the maximum static friction, and sure enough, it's bigger than how much force is getting applied in the opposite direction. So it doesn't move. Okay, so that's actually a very interesting consequence. If someone gives the crate a small push of how much, it will break loose. What will its acceleration be then? Okay, so this is even something different than what we did before. If it just breaks loose, so let's go back to the paper. If it just breaks loose, that means I had to have been applying 52.5 newtons of force. So that means Fx would be 52.5 newtons, right? And if it just breaks loose, that means it's in motion, which means I'm dealing with a dynamic friction now. So Fd is equal to mu times the normal force. Now the normal force we already found was 70 newtons. So keep in mind that's newtons, this is normal force. So just be careful with that. And the coefficient for dynamic friction is 0.60. So we have 0.60 times 70, and that's equal to 42 newtons. So we have a dynamic friction force of 42 newtons. Notice that that's considerably less than 52.5, right? And that's what we said before. The dynamic friction force will be always less than the maximum static friction force. Okay, so we've got this, and we can see that our applied force is 52.5. So if you can imagine a very simple scenario, if you were just dealing with Fx and FFD, or FD, you would really be only dealing with those two forces in the horizontal direction. Obviously, this is not a true correct free body diagram, but just to give you an idea. Right? So acceleration, in order to find that, acceleration is the sum of the forces, in this case in the x direction, divided by mass. So we have Fx minus FFD divided by mass. So Fx is 52.5 minus FFD, which is 42, divided by mass, which we initially found in the problem to be 10.2, right? Okay. So 52.5 minus 42 divided by 10.2, that's about 1.03 meters per second squared. Okay, so that is it. All right, so that is the solution to this problem. That is the acceleration. Let's just stick a direction in there too. It's going forward, or we can just say in the positive x direction. Both of those are acceptable. Okay. Let's go back to the slides. So we finally arrive at Newton's third law. So let us just quickly remind ourselves, Newton's first law is the law of inertia that says an object wants to keep doing what it's doing unless acted upon by an external force. So in other words, if something is at rest, it will remain at rest. If something is moving in uniform motion, it will remain in uniform motion unless acted upon by an external force. Newton's third law says that for every action force, there is an equal and opposite reaction force. Okay, so this is how you would show it using symbols. Fa sub b is equal to minus F sub ba. What this means is the force of object A on object B is equal to the force of object B on object A, but with a minus sign in front. And the minus sign just means it's going in the opposite direction. So the magnitudes of the forces are the same, but the directions are opposite, just as we know that negative east is equal to west. Okay, now based on this, if every force gets canceled by another force, then technically the sum of all the forces in the universe should be zero. Okay, but then why are there accelerations? And the answer to that is because each of these forces acts on a different object. Understanding the statement in red on this slide is going to help you with a live discussion question this week. All right, when you push on a door with 10 newtons of force, the door pushes you back with exactly the same 10 newtons, but in the opposite direction. So why does the door move and not you? Okay, so some of you might say, well, okay, so here's my F applied. So I am applying a force onto the door, and that's my action. The door applies a force back on me. That's the door's reaction, hence action-reaction pairs. But why doesn't the door move? And some of you might say, well, the door is lighter than you are. And sometimes that's true, but imagine you are opening a very heavy metal door. It might actually be more massive than you are. So in that case, why don't you move? Why does only the door move? And that's because you have your feet on the ground. You can resist the motion of the force pushing you back, but the door cannot resist the motion. It's on hinges, so it's going to rotate in the opposite direction. Okay. So the door can't resist the force, but you can resist it. That's the main idea. Okay. Consider a baseball resting on a tabletop. Discuss each of the forces acting on the baseball and the associated reaction force. All right, so whether or not the baseball is in contact with something, there's always going to be a weight associated with it. There's a force of gravity. And that force of gravity is the ball on the ball due to the earth. So FBE. And that is true whether it's on the table or not. So let's say it's on the table. You still have the force acting on the ball due to the earth, but now the table is also acting on the ball. So you have N sub BT. But what are these action force pairs? Okay, the fact that you have a normal force on the table, on the ball due to the table is because the ball is exerting its weight on the table. So in a sense, it's almost like it's exerting its own normal force. Okay, so the normal force on the table due to the ball. So those two are action-reaction pairs. But what about the force of gravity on the ball due to the earth? Well, there's actually a force of gravity on the earth due to the ball, and it has the same magnitude as the force of the ball towards the earth. Now, while these two are also action-reaction pairs, notice that the letters are different, they have the same magnitude in opposite directions, they're acting on different sized objects, and that is significant. Remember when we first started learning about Newton's second law at the start of this video, we said that if two objects have the same force acting on them, or at least the same magnitude of force, the acceleration will be substantially less for the object that has a lower mass, right? And that's exactly what's happening here. Okay, now whenever you work with Newton's third law, you have to be able to identify action-reaction force pairs. And so usually when you have a collection of objects that are colliding or exert forces on each other, you have what's called a system. And a system is just a collection of more than one body, which is mutually interacting with the other bodies. All right, so imagine 3 billiard balls. Okay, so this white ball is called the cue ball, and the goal of this game is to get the colored balls into the pockets. Okay, so if you hit the colored balls, I mean, they're going to go off in some direction, but the white ball imparts a force onto the red ball, and it imparts a force onto the blue ball. In return, the blue ball imparts a force on the white ball, and the red ball imparts a force on the white ball. All of those little forces are called internal forces. And for any system, internal forces always cancel. Now, I'm going to give you another example of what would be considered an internal force. Imagine you have a box sitting on a floor. What is that box made up of? Well, it's made up of atoms, right? So atoms comprise this box. I mean, I can just keep filling this in with circles, but you get the idea. Now, what are atoms made up of? Well, they're made up of 3 primary subatomic particles, the protons, the neutrons, and the electrons. And there's obviously more than 3 of them in each atom of this cardboard box, but we'll just draw 3 for now. Now, each of these atoms experiences forces with the other atoms in the box. Likewise, if you go in even deeper, the electrons and the protons, they also experience forces between one another. The neutrons as well, there's a force there too, which you'll learn about later on. But the idea is when really you look at a box, what do? You don't care about all those internal forces. You care about the external forces. Is there an external applied force? What is the force that the floor exerts on the box? What's the normal force? What's the weight? What's the force of friction? These are external forces. These would be internal forces, and they always cancel out. Now, when we say internal forces, we don't always just mean the atoms or the particles that make up an object, a solid object or a liquid or a gas. Sometimes internal forces are simply forces within the system. So in the case of the billiard ball, the white cue ball hitting the red and blue balls, you have the force of the white ball, symbolized by the white arrow, hitting the red ball, and the red ball in turn hits the white ball and, well, doesn't hit it, but it imparts an equal magnitude opposite directed force back on the white ball. Okay, the white ball also hits the blue ball and imparts a force, symbolized by the white arrow. The blue ball in turn imparts an equal magnitude opposite directed force back on the white ball. Okay, so these are the internal forces in the system, and they all balance. Okay. External forces are the forces that the balls feel from external origins. Like I mentioned when I showed you the page, this would be something like their weights, their reaction forces, also known as normal force, the cushion forces, and the acoustic forces. Okay. There might be some friction there too, but any of those would be considered external. Anything inside that all balance out, we call those internal forces. All right, that is it for video 2.2 Forces, part 2 of 2. Thank you for watching.